Okay then, so I'm going to go through the higher tier topic test paper for stars and planets. Question 1, the boxes on the left show the names of objects in the universe. The boxes on the right is the time taken for light to travel from these objects to Earth. So we're looking really, this question is all about knowing what's in our universe and relative sizes. So we got the sun, we got the moon, we got a galaxy, and then we've got a star within our own galaxy. So we need to now look at the moon and think, well, that's the closest to us. And then the sun is the next closest to us. And then we've got a star in our galaxy. And then another galaxy is going to be furthest away. So I haven't drawn lines, even though it's asking me to, because I think it looks quite confusing. By the way, if you're ever asked to draw lines in an exam, make sure you draw the lines and don't do what I've done, even though I think that looks clearer, because they might mark you down for not following the instruction. So I've got the sun here as 500 seconds. I've got the moon, which is closest, so that's 1.3 seconds. So it takes light 1.3 seconds from the moon, then the sun, which is the next closest thing. Then it's going to be the star from our own Milky Way, which is 4.5 years, and then another galaxy, which is over 2 million years. So big distances there. Then we go to question 2, and again, it's another matching up question. So draw lines from the names to the left of the box and put them in order. So this is the life cycle of a star. We're looking for the stages here. Again, I've been really naughty and not done what the questions asked me, but I think it looks clear like this. So this is going to be your stage 1 main sequence star you can start with out of these options. Then it's going to go to a super red giant, a red supergiant. Then we're going to go to a supernova and then into a black hole. So obviously this is a star much larger than our sun. So this is the biggest star we can get because it ends in a black hole. Question 2b then. So it's showing you now the gravitational force acting in on a star, so pulling the star in. But what's acting against that is gas pressure, or we can say radiation pressure, is going to be the stuff that's acting against gravitational force. And this is kind of going to link with when we do Newton's laws, because this star is a main sequence star, and it's balanced. The forces are balanced there. And then C, you use the words to fill in the blanks. So main sequence stars generate energy by fusion, not fission. Fission is the splitting, and fusion is the combining of atoms. So of hydrogen into helium. So it turns the most abundant gas, hydrogen, into helium. The second most abundant, and it's number 2 in our periodic table. This is number 1, hydrogen. Number 2 is helium. Heavier elements are created when stars are much larger than our sun collapse. These heavier elements include uranium. Now, you could be blamed thinking, well, iron as well, but read on with the sentence. These heavier elements include uranium, which we use in our fission reactors on Earth. And that's sort of a radioactive material that we use to generate energy. And we only have elements heavier than iron then because they are created during a supernova explosion. So that's the order there. Question 3 is a numeracy question, really. Okay, it's hard to teach this because it does rely on your sort of understanding of interpretation of the question and then using that to answer these questions. But I've underlined there that the center of our galaxy is 30,000 light years away. Now, if we know a light year is the distance traveled by light in 1 year, and it says that 1 light year is the distance, not the time, the distance traveled by light in 1 year, we can start answering these questions. How long does it take to travel? How long does light take to travel for us from the center of the galaxy? Well, it just said there, the center of the galaxy is 30,000 light years away. So it's going to take 30,000 years because, again, it's the distance traveled by light in 1 year. And I know that's hard to get your head round, but it is what it is, okay? It's really hard to teach problem solving. How long does it take to travel from the sun to the Earth? Well, it says there 1 AU equals 8.3 light minutes. So it's going to take light 8.3 minutes. Okay? So if light... So again, it's just referring back to what we know. All right. 1 light year is the distance traveled by light in 1 year. 1 AU is the distance between the Earth and the Sun. 1 AU equals 8.3 light minutes. So how long does it take from Sun to the Earth? It takes 8.3 minutes. Light takes 13 hours to travel from Pluto to Earth. What is the distance? The distance traveled by light in 1 year. So it's going to be 13 light hours. Again, it's hard to get your head around, I know. And then Mercury is 0.4 AUs from the Sun. Venus is further than Mercury from our Sun, but not as far as Earth. Estimate the distance. Okay, so here's my little diagram. I've got Mercury there, which is 0.4 AUs. 1 AU is the distance from the Earth to the Sun. So that is 1 AU. So we're looking for a number between 0.4 and 1. And that's why I've got anything bigger than 0.4, anything lower or less than 1 there. So you could say 0.5, 0.6, 0.7, any number between these. But don't say 0.4 and don't say 1. Okay? Next question is, name the 2 gases. This should be, for 2 marks, I think that's, very generous. Hydrogen, helium, we find in a star. This one, a little bit more tricky because you've got to kind of work out the different stages now. So our Sun is a small star, so it's going to end with a white dwarf, and therefore we use the red giant. And then the massive star is going to include a supernova, which this is not going to have, and a black hole, which this is not going to have. So you use these words, to fill in the blanks there. So for 4 marks, again, very generous. Brings us on to question 5 then, the Hertzsprung-Russell diagram. Let me just straighten that up. So, estimate the surface temperature of our Sun. You can see I've drawn a line up there, or line it down, I should say, from our Sun. And I'm just estimating the temperature there. I think it's round about halfway. Okay, maybe slightly to the right, but I've said 6,000, and that's fine, because the mark scheme will accept anything from 5,500 to like 6,500. So you're looking just an estimation, a range there. State 2 differences between the properties of Alpha Centauri b compared with our Sun. Well, let's have a look where the Alpha Centauri b is. I've circled it there. Okay, so it's more right on the graph. Remember now the temperature is getting smaller. So it's going to be cold, it's going to be cooler, it's going to be lower temperature, and it's down on the y-axis, so it's going to be less bright, so it's going to be dimmer. So it's lower. So I said lower temperature and dimmer. State one way, our Sun and Alpha Centauri are similar. Well, they're in the main sequence trend. So this is the main sequence trend there. So they're both main sequence stars. The red giants tend to hang around up here, and then the dead stars tend to hang around down here. What changes will happen in the Sun to cause it to expand? Well, radiation pressure is going to increase. It's going to overcome the gravitational forces. Okay, so radiation is more than gravity here. Use information from the diagram to describe the effects of these changes they'll have on the Sun. So they're going to become larger, they're going to become brighter, they're going to get cooler, they're going to get redder. And you can use the diagram for that. Look, you can know they're going to get brighter, but they're going to get cooler as well because they move to the right. Remember, this scale is a bit odd because we start with hotter up here and we go cooler. So it's not like the other graphs. And then it says mark X where the Sun will end its life, and I've put a little X there. Okay, it's gonna happen around the white dwarf area. Okay, maybe my X should have been more towards these lines, but I wanted it to be clear on the diagram. So I'm going to get a mark so long as it's to the right, to the left of the main sequence stars and down the bottom, somewhere there.